answer is that if you work things out, the coherent state actually looks something like this. It's a linear superposition of photon number state, e to the minus alpha squared over 2, and it's equal to 0 to infinity, alpha to the n squared root n factorial. So the coherent state is a linear superposition of the photon number state. That you can find from your homework by just doing this exercise. Okay, finding all the Cn's will have that property. And now if I substitute in the coherent state in this density operator, I just substitute it 2 times, I get this to be equal to e to the minus alpha squared. And then I have 2 sums. Alpha to the n, alpha star to the n, because I have this conjugate transpose here, divided by n factorial divided by n prime factorial. Okay? And when I do the outer product, I will have n prime. Okay, so the density operator looks something like that. Okay? This is if you have a coherent light. Okay? If you have a coherent light, this is how the density operator should look like. And this density operator will consist of the diagonal term as well as the off-diagonal terms. But if we have a thermal light, the thermal light should be expressed by a quantum state. Which is a linear superposition of photon number states, but then all these photon number states are incoherent with respect to each other. Then the density matrix for incoherent light should be expressible as only the diagonal terms. The off-diagonal term should be 0. Okay? This is thermal light. All the off-diagonal terms are 0. Are there any questions on that? There's no off-diagonal terms in the second representation, whereas in the first representation with the density operator, we have the off-diagonal terms. Okay? So we have to invoke Boltzmann law. Boltzmann law says that if something is in thermal equilibrium, if a state is in thermal equilibrium, then the probability of finding the system in that state is proportional to the energy of that state divided by kBT over Z. Z is a normalization factor, so that sum over n is equal to 0 to infinity equals 1. Okay. This is a probability distribution, and the probability of finding the photon number state with energy E sub n to be in this state. This is Boltzmann's law. Okay, this is known as okay, and it can be derived from thermodynamics and statistical physics. But let's see if it makes physical sense. Let's do a sanity check on this law. What it says is that if the energy of the system has very high energy value, okay, it's very unlikely that the system is in that state. Then the probability of the system to be in that state is very small. If the system has very low energy, then if this system is in thermal equilibrium with the environment, then it has a high probability to be in low energy state. So it satisfies our sanity check. Okay, in terms of sanity check, it satisfies. So, but you can derive it using statistical mechanics. But it makes a lot of sense. And in order for this z to be a normalization constant, then z is just sum over the numerator. Okay, sum of the numerator. And if you take z to be that, then this is always true. Okay, this is just used to normalize that. This is called the partition function. Okay? So, you can actually sum z in closed form for photon number state. For photon number state, the energy is given by that. Okay, you have a photon number state in the quantum harmonic oscillator. Now, if you imagine the quantum harmonic oscillator to be in thermal equilibrium. Okay, this is in thermal equilibrium with the background bar, thermal bar. Then this quantum harmonic oscillator will absorb energy from the environment. It also gives out energy to the environment. That's what thermal equilibrium is. Okay. So if you look at this quantum harmonic oscillator, then the energy of the quantum harmonic oscillator will be distributed according to Boltzmann law. Okay, those photon number states with high energy value will have less likelihood of being occupied. But the photon number states with low E sub n will be most likely occupied. And if you plug this into the partition function, then you can show that this is equal to half h bar omega over kBt, sum over e to the minus n h bar omega over kBt. N is equal to 0 to infinity. Okay, you can sum this. This is just x to the n. Okay, x to the n. X is e to the minus something, and then you can sum this to 1 over 1 minus x kind of thing. And if you sum that, then you have this in equal to half h bar omega over kBt. And you sum this, it becomes something in the denominator. 1 minus e to the minus h bar omega over kBt. Okay? And then you can rewrite this. I can rewrite this with this in the numerator too. Okay? So then if you plug that in, then you get p sub n. P sub n to look something like this. P sub n is equal to e to the minus n. You put this into the numerator. You put this number into the numerator. Okay? You get this half thing cancel out, and then you will have just this times 1 minus e to the minus h bar omega over kBt. Okay, so p sub n will look something like that. And then if you look at the average number of photons you have in the quantum harmonic oscillator, the number of photons that you have will be number of h bar omega that you have. Each photon is counted as 1 h bar omega. So number of photons that you can have is just n times p sub n, and you can sum over n to 0 to infinity. For this is the probability of finding the photon with this number, and this is the average, and you can sum this, and then you can sum this to be n is equal to 0 to infinity, and then you can plug this in here. Okay, you can see that this is equal to something like x to the n times 1 minus x kind of thing. If you let x be that thing over there, you can sum it, and after summing it, so you can have this actually. No, sorry. You can sum this. Okay? You can sum this very easily. Actually, you actually have to sum something like this. You know how to sum this, right? since we know how to sum this, you know how to sum this. You just sum this by taking its derivative with respect to x. If it differentiates with respect to x once, it brings in the thing. So you can sum this very easily. And then this will sum to x over 1 minus x is the answer. And then after you plug in back x, you have this. Okay? So the average number of photons that you have in this quantum harmonic oscillator will be that number over there. And then average energy will be n h bar omega. Average number times this will be h bar omega over e to the h bar omega kBt minus 1. Okay? So this is actually Planck distribution. This is what the Planck distribution. It was first guessed by him. He didn't even derive this. He looked at the radiation experimental data. He guessed this distribution law in order to fit this experimental data. But now we can derive it quantum mechanically. Okay, the average energy that you have for the quantum harmonic oscillator is going to be this. Then, how do we get the radiation law? Planck's radiation law coming out of this. Okay, you have to do a little bit more work. Let me just do that. And then you have to, it might be interesting to notice that this is just equal to kBt when h bar omega tends to 0. Okay? This is the average energy, the kinetic energy or the total stored energy of a classical harmonic oscillator. A classical harmonic oscillator has both potential energy plus kinetic energy. So each of them get half kBt according to the law of equal partition of energy. So the total energy of this harmonic oscillator in the classical limit is actually equal to that. So that agrees with what we have. Okay? But then, in order to understand Planck's radiation law, we can think of a box of volume V, okay, and then calculate the number of modes per K volume, delta K volume, because this would give rise to quantization in the K space, okay, this quantization values in the K space. If you look at the periodic boundary condition thing and then you will give all these quantized modes, you'll find that delta n that you have, we have done this quantization for electrons before in the box, but now it's photon in the box. Okay? Photon in the box, this is like the number of states you can find in an annulus region. Okay? A spherical shaft. This is the volume of the spherical shaft, and this should be 2 pi cubed. Okay? And then the size of each cube is actually 2 pi over Lx times 2 pi over Ly times 2 pi over Lz. Okay, if you remember the electron case, you might have Lx, Ly, Lz. If you have a box of this size, if you impose the periodic boundary condition, it will discretize all the modes that it has, and size of each mode is roughly equal to that. Okay, delta K cube is roughly equal to that. The size of the cube, the little cube occupied by each mode, is about that size, and hence the number of modes that you have is given by this number over here. And then you can convert this to frequency, 4 pi omega squared delta omega over 2 pi cubed over c. Okay? So the number of modes you have in a small frequency interval is given by this number. Okay? And then you can simplify this to be V omega cubed it should simplify to omega squared or omega cubed. Pi squared c cubed. Okay, that's what I have over here. This should be c cubed over here. It simplifies to that number. Okay, now if I look at each of these modes is a quantum harmonic oscillator. Okay, it will have this energy over here. So the energy will be h bar omega over e to the h bar omega over kBt minus 1 times this v omega squared delta omega over pi squared c cubed. Okay, so if h bar goes to 0, this will be kBt v omega squared delta omega over c cubed. This is known as the Rayleigh-Jeans law. This is known as the Planck's law. Okay, if you look at these two laws, before quantum mechanics was postulated, it says that the energy density per unit frequency interval will grow with frequency. As the frequency gets higher and higher, there will be more energy in the system. Okay? So what it says is that if you have a cube in thermal equilibrium in its environment, classical law says that the higher the frequency, the more energy will come out of this system. Why is that so? Because when the frequency gets very high, there will be more and more modes. The density of states goes up. We have counted this number of modes per unit volume. It grows as omega squared. Okay, so the number of modes per unit volume grows bigger and bigger and bigger. Okay, and then it grows without bound. So if you look at the energy, the ED omega, classical law says that it will go without bound like that. And that was called the catastrophic breakdown, which never happened. Experiment always shows that after a certain frequency, it comes down. And Planck postulated this distribution. Okay? And why is this? What is the physical reason that the energy has to come down as the frequency goes up? The reason is because of Boltzmann's law. As the frequency goes up, if you look at the quantum harmonic oscillator, the energy level becomes bigger and bigger, and this is proportional to h bar omega. As the frequency goes up, this quantization energy is going to go big, and what this says is that Boltzmann law says that only the low energy state is going to get occupied. The high energy states are not going to get occupied. So the number of photons that you have becomes smaller and smaller as the frequency goes up, because only the low energy states can be occupied. So even though the number of modes becomes more and more, the number of photons per mode becomes smaller and smaller, because the higher energy states are less likely to be occupied. Okay? And that's why we have this thing that comes down to prevent the catastrophic ultraviolet breakdown in Rayleigh-Jeans law. And Planck's law was successful in predicting the radiation that comes out. I'll stop here and give you a 5 minutes break, and after that, I need to take a, yeah?
In the electron case, we consider spin degeneracy, but do we consider mode degeneracy right now?
Yeah, we actually have to consider the mode degeneracy. There should be a factor of 2 somewhere. Let me see the factor of 2. Yeah, I might have put in a factor of 2. I just sketched it. If I put in a factor of 2, for the 2 polarizations, I have 2 modes for 2 polarizations per mode. Okay, that would be a factor of 2 difference, and things will come out correct. But then I don't have this really Jeans law catastrophic breakdown. This is very important, and this entirely is a quantum effect, quantization of energy level. Okay. Yeah. Thank you for pointing that. There should be a factor of 2 coming out somewhere. I write this out carefully, and then we have a 5 minutes break. Any other questions before we take the break? Yes.
We don't really get a picture of this thing. So you're trying to say as the volume is bigger and bigger,
Right.
and the number of modes in per case space is getting smaller.
Right. You notice that the quantization, the delta k that we have, this delta k that we have in the k space is proportional to, inversely proportional to the size of the volume. Okay. The larger the volume, the smaller delta k is. Okay. So the number of modes you get per k volume, this is a k volume in the k space. Okay, will become more and more. You get more and more modes for k volume, for annulus region. Okay, how many modes can you have in this shell? You will have more and more modes as the volume gets bigger. Okay, and if you convert this to frequency, it says that it will go as omega squared. As the frequency gets bigger, k gets bigger. K is omega over c for photon, but k was something else. K is something like h bar k squared 2n is equal to E, right? For electron. This is electron, right? This is electron, this is photon. This is h bar omega, right? So for electron, it was like this. For photon, it is like this. K and omega are related quite differently. So there's a linear relationship between k and omega in photons, but the relationship is quite different in the electron. And when we plot the density of states, we have to put in this squared behavior because of this relationship. But then in photon, it's just this linear behavior. Okay? And then if you go through that, you get the black body radiation law, which is Planck's law. Okay, we take a 5 minutes break here, and then we come back and I can take over.